Welcome everyone. I'm going to be speaking about UMAP, Uniform Manifold Approximation and Projection. But first, quick, who am I? I'm Leland McInnes. I'm a researcher at the Tata Institute for Mathematics and Computing. I'm the maintainer of a variety of machine learning packages, UMAP Learn, HDBScan, Pioneer Descent, and others. And I'm also a contributor to scikit-learn and scikit-TDA. Okay, what is UMAP? UMAP is a dimension reduction technique that takes its motivations and theoretical underpinnings from topology. That's a bit to take in, so let's break that down. Let's just start by working out what dimension reduction is in very general terms. So when we talk about dimension reduction, we're talking about finding the latent features in your data. What are these latent dimensions? Well, they're sort of the reduced set of things, and feature engineering is important. Visualization matters. So often a lot of the dimensionality in your data is kind of redundant, and getting rid of it helps with both feature engineering or visualization. So let's take a quick look at a couple of examples just to get an idea for some high dimensional data and why it might require fewer dimensions. So this is the first 100 of 70,000 samples from MNIST digits. These are 28 by 28 pixel grayscale images of handwritten digits. Each pixel counts as a dimension, so in total we have 784 dimensions. And surely we don't need all of those to reasonably well describe handwritten digits. How many dimensions do you think we could get away with and still capture most of the structure in a data set of handwritten digits? Some good guesses, and we'll come back to this later. As another example, Fashion MNIST is 28 by 28 pixel images of fashion items. So dresses, shirts, boots, shoes, bags, etc. And again, we probably don't need all 784 dimensions. These are a little more complicated than digits, so maybe we need a few more, but we'll see how it goes. So let's see what happens if we run UMAP on this with the full 70,000 MNIST digits dataset. And here we're going to go from 784 dimensions down to just 2, which is probably less than you guessed was required, but we still do a reasonably good job. Each point in this plot represents a handwritten digit, and the points are colored according to which digit they were supposed to represent. And you can see that even with this really drastic reduction in dimensions from 784 down to 2, we've still captured a lot of the important structure and information. Similarly, here's Fashion MNIST, and you can see even though 2D is perhaps a little too compressed here, we're not getting everything right, we've still captured a lot of the different structure in the classes, and things like trousers and footwear are reasonably separated out from the other kinds of fashion items you might consider. All right, so how else has UMAP been used? Well, it's actually seen a wide variety of applications. UMAP's been used very successfully in helping to analyze how deep neural networks work. This is an example for the Activation Atlas, which looks at how image classification networks see when they look at images. But it's also been used to analyze NLP-based networks like BERT. And in general, the idea is always to take the complex, high-dimensional internals of what's going on inside the neural network and allow a user to be able to see, to some extent, what it's doing. Here's another example, Open Syllabus Galaxy. And this is visualizing over 1 million textbooks based on the different university syllabi that they're listed in. The result's a giant map of textbooks with similar and related books forming continents and islands. And it's well worth visiting the website. It's fully interactive. You can zoom in and explore. And to be honest, it's just a great way to find new and interesting books. And yet another example, this one interested in more than just the visual representation, UMAP was used to play a role in producing lower dimensional representations of birdsong spectrograms. So this helped a great deal with clustering them into distinct syllables. And then the authors could look at the paths through the syllable space to understand how the songs are arranged and how that compares to the way human speech is composed together. Okay, so clearly dimension reduction is useful. And I said at the start that the theory is based on topology, which is, relatively speaking, a fairly abstract and obscure field of mathematics. So the first question you should ask is, why is topology relevant to this question? All right, let's start by comparing classical machine learning with programming. With programming, you collect a whole bunch of data and some rules, probably via requirements gathering, and you write a program that allows you to turn that set of data and rules into the results you want. And it's important to just frame that because it contrasts with machine learning, where instead what we get is the data and the results we want to get out, and we push that into a machine learning model system, and it produces the rules that we would want from the programming. But, and this is the important point, dimension reduction doesn't fall in the world of classical supervised machine learning where we get handed those results that we want to get. It's what's known as unsupervised learning. And in this case, we don't have a predefined answer that we want to get out. We just get given the data and have to produce results of some kind. And so unsupervised learning in general amounts to outputting something about the structure of the data. That might be cluster structure from doing clustering, or density structure from some sort of density estimation technique, or maybe just lower dimensional representations from dimension reduction. With no labels or rules to guide things, what's going to determine any structure is how individual samples from your dataset compare to each other, what makes two samples similar and what makes them different. And ultimately, dissimilarity is going to look a lot like a metric from mathematics. It may lack some, or to be honest, even all of the properties of a metric in the strict mathematical sense, but various relaxations of classical metric spaces are very much the flavor of what's going on here. So in other words, what we care about for unsupervised learning is geometry and ways to compactly summarize and describe that geometry. We also have to be willing to accept that we might not actually get a nice perfect metric, and so we need to be able to cope with geometry in a flexible way. And this is almost precisely what topology is about. So let's talk about topology and how it might apply to database tasks like dimension reduction. First off, what is topology? So here's the Oxford English Dictionary definition. We care about both the definitions here, really. First of all, we care about the strict mathematical definition because we're going to make use of that. But the latter definition, the way in which the constituent parts are interrelated or arranged, that really matters to us too. That's what this is all about. So what we're really caring about with topology is the relative interrelationships between points. So exact distances are not important. And what that means is that this lovely cute cow is actually equivalent to its spherical cow representation here. We've retained the relative interrelationships, if not the distances. As long as we can continuously deform from one thing to the other, we're okay. But this kind of view of topology makes heavy use of the continuum and infinite sets are kind of hard to deal with, especially on a computer. Also, since we're talking about data analysis, it's worth noting that we very rarely get an infinite amount of data to work with. So what we need is a way to reduce things down to a finite number of key marker points and just designate continuous spans between them so that we could make everything much simpler and ideally finite and combinatorial. And this brings in the basic tool from topology, which is known as simplicial complexes. So the real idea here is we can build things up combinatorially, and then once we have the pieces, glue them together. So here is from simplicial complexes, what's known as a one simplex. It's just defined as a one-dimensional span between two zero simplexes, which are just points. But we don't need to actually keep track of that continuous span. We can just take the set of zero simplices and assume that it spans them. And likewise, we can define a two simplex as the span of three zero simplices, bounded by one simplices. A 3 simplex is a span of 4 zero simplices and is bounded by 4 2 simplices, and so on. Again, we're representing each not by the actual continuous span, not by the actual geometry we see, but just by the very finite sets of zero simplices that define those spans. Now, if we start with an arbitrary set of points, call them zero simplices, we can choose particular pairs and define 1 simplices between them. And then we can choose particular triples and define 2 simplices spanning them, as long as we've got the 1 simplices that bound it, and so on. And in this way, we can build up much more complex structures. So it turns out that you can build pretty much any topological space up to a few pathological cases. Well, I guess technically an infinite number, but it's a very small infinity. And in general, all we're doing with these spaces is picking out different subsets of sets of zero simplices and declaring them to be simplices as well. So everything's purely combinatorial, no geometry required. So an important step here is we're moving from continuous geometry into something purely combinatorial. And this shift in viewpoint is a very powerful way of changing how we look at the data. I want to go a step further because this shifting in viewpoint type approach is something that I'd like to emphasize. This isn't strictly necessary for what follows, but I think it helps emphasize how we can turn these viewpoints around in different ways. So we can define the notion of face maps for n simplices. For a given n simplex, there are n+1 associated face maps mapping to lower dimensional simplices. And the ith face map is simply the one that leaves out the ith zero simplex from our set, giving us a simplex 1 dimension smaller. So the 0th face map of this blue-red thing, we just leave out the 0th item, the blue vertex, we just end up with a red vertex, and so on. We can do the same with 2 simplices and leave out various different 0 simplices and get just the 1 simplices that bound it in turn. And so we're doing this purely combinatorially, and this is nice, but these face maps provide the combinatorial glue for simplicial complexes. We can flip the whole thing around and actually take the simplices themselves as primitive objects, not composed of 0 simplices, but simply things in and of themselves. And so switching to a category theoretic point of view here, we can have a set of 0 simplices x0, a set of 1 simplices, not made up of 0 simplices, just a set of objects that we're declaring are 1 simplices x1, a set of 2 simplices x2, and then we have all these face maps chaining together, linking them. And defining those face maps defines how to glue this simplicial complex together. So what was this nice purely combinatorial thing that we could then imagine geometrically can instead be turned into something that we can apply pure category theory or algebra to. And again, this shift in viewpoint allows you to apply different kinds of tools to the problem. So it furnishes us with a lot of algebraic and combinatorial tools to work with topology in general. So while, as I said, some of that last bit is not strictly necessary for understanding how UMAP works, I wanted to really highlight how this change in ways to view the problem was useful in designing the algorithm in the first place. All right, let's talk about applying simplicial complexes to data. How can we do that? At least one way is via check complexes. And these are actually pretty general, but I'm going to describe it here in a very data-centric point of view. So suppose we have some data and some notion of dissimilarity between the samples. Here, I'm just going to take Euclidean 2 space. The distances are as you see them on the page. And we're going to create balls about each sample of some fixed range of similarity. And these balls are going to cover our data. Whenever 2 such balls intersect, I'm going to create a 1 simplex between the data samples. When the balls are very small, as they are here, they're just slightly bigger than the points. Very few of these edges are created, and it doesn't really do much. But once we make the balls a bit larger, we get more intersections, and we'll add more simplices as well. Whenever we get a triple intersection of balls, we're going to add a 2 simplex. And whenever we get a quadruple intersection, we're going to add a 3 simplex, and so on. And as we make the balls larger, we get more complicated and higher dimensional simplicial complexes forming, until we reach a point where we've actually captured a lot of the topological structure of the data quite successfully. Now, this is a relatively successful proof by picture, but you should be wary of that because pictures and toy data sets are often very deceiving for how things are going to work in practice. But what we do have is a theorem from algebraic topology. For our purposes, you can take this to be a picture of a theorem. That's why I put it in a frame. Don't worry about the details. What you need to know is that it says that if you have a good cover of one of these topological spaces, then the check complex that we form, called the nerve of that cover, will actually be equivalent, after some topological fudging, to the original space. In other words, by applying this process, we can actually recover the original topology that we care about. So check complexes preserve the topological information we're interested in from the underlying space that the data was sampled from. All right, now that we have some preliminaries out of the way, let's look at how UMAP actually works at performing dimension reduction. So let's take some points color-coded by their position in the manifold from which they were noisily sampled. The underlying space is a sine wave, and topologically, the space is really just a line. We can straighten out the wiggles from a topological point of view. We can build a cover by placing open balls of some radius on each point. And now we build the check complex. We didn't get what we wanted here, though. Why not? Well, it turns out our cover wasn't good in that it didn't really cover the space in the way we wanted. There were gaps in the cover where we didn't have overlaps, and other regions where the cover clumped up a bit much. So going back to our picture with the open balls, you can see the teal balls in the middle there are not covering the span between some of those points where we imagine the manifold actually lies, that if we sampled more data, we'd see more points along that span that the balls don't cover. And likewise, in the bottom right corner, you can see a region where all the balls clumped up just rather too tightly, just because the data happened to be sampled a little more densely there. So we can't get any consistent size of ball around each data point that's going to work everywhere across the data. So the catch was in the distribution of the data. We didn't cover some parts of the manifold because points were sparse there. And we also have clumps because points were too dense there. If the points were uniform across the manifold, then this would work great. So here's that same manifold now with the points uniformly sampled from it. And you can see that the result of taking the nerve of this cover with nice fixed size open balls are going to give us pretty much almost exactly what we want in terms of recovering the topological structure that we're interested in. But when is data that nicely behaved? That's not going to happen in practice. Well, let's start with making an assumption. Let's just declare it true and say that the data is uniformly distributed on the manifold. Now, that's going to have a catch because it means something has to be true of the manifold for that to end up being the case. And what it means is that our notion of distance on the manifold is going to have to vary and not simply be inherited from the ambient space. So one way to think about this is that manifolds are locally Euclidean, and different patches map to Euclidean space in different ways. So accordingly, the metric or the measure of distance can vary across the manifold as well. We can exploit that and estimate different local metrics for each data point so that the data looks uniform with respect to the varying local notion of distance. And we're going to throw in another assumption here, and that's that the manifold is locally connected. If you like, one way to think about this is it's just ruling out a whole bunch of those pathological topological spaces that we shouldn't really be seeing coming from data, but that would mess up some of these other bits and pieces. Okay, what we're going to end up with is a cover that looks something like this. We're going to be confident out to our first nearest neighbor so that we're locally connected, and then fuzzy as our confidence in the local metric declines. But there was a catch. All our local metrics were incompatible with each other. We approximated different notions of distance for each point, and there's no reason that a pair of points are going to agree on their distance to each other. In fact, they're not. And this is where background theory comes to the rescue again. Again, here's another picture of a theorem. But what is going on here is we're making use of some of that change of viewpoint. We're switching from a geometric view that was stretching towards a combinatorial one and shifting that into that category theoretic algebraic view, and finding that within that framework, there's a very simple way to resolve these problems. It turns out there's mathematics that solves all of this for you and tells you how to do this combining. If you have a family of simplicial sets, which is what we're going to get in this translation to this other viewpoint, how do you glue them together? It turns out there's a natural answer called colimits, and that's the natural maneuver to make here. Whether that math makes sense to you, that's not really the relevant point. What matters is by changing the viewpoint, we can find an incredibly natural answer that solves what was an otherwise tricky problem that had potentially significant arbitrary choices involved. And this provides us with a nice weighted simplicial complex. But equally importantly, there's good theoretical justification for why we want to construct this graph, with the decisions all made by the underlying theory. So now we need a low-dimensional representation of this. Let's suppose just for a moment that we were handed a low-dimensional representation of the data. How would we be able to tell if it was any good or not? We'd need some way to compare it to the original. Well, seeing as we really care about the geometry, topology, structure of the data, let's apply the same process and get a fuzzy simplicial complex associated to that low-dimensional data. Now we're just representing the topology in a nice finite combinatorial way, and we have nice algebra to compare these things. So we can measure the distances between these complexes using fuzzy set cross entropy, seeing as we have fuzzy simplicial sets here. And it's a nice measure that looks at how much the low-dimensional representation differs from the high-dimensional one. The formula looks like this, and the key part here is that when we have a high probability of edges existing or simplices existing, in the left-hand term, we want the ratio of existence of probabilities to be close to 1. So we want those points close together in the low-dimensional representation. Conversely, where we have a low probability of the edge existing in the high-dimensional space, we want a low probability in the low-dimensional space too. And these two factors are going to provide some push and pull. And now that we can measure how good our representation is, we can see with respect to this push and pull how to make it better. And that means we can turn this into an optimization problem. And so really, the left-hand term says, pull all these points together, push these points further apart, and iterating that over all the points, we can slowly move towards a representation that's doing the best job it can of reproducing that same topological structure when we consider it in that way. And that means that we can run an optimization algorithm to steadily improve our low-dimensional representation. Thus, even if we start with a bad low-dimensional representation, like say a random one, or one based on the Laplacian of the graph, we can steadily improve it until we get a good one. And that, from a theoretical point of view, is the algorithm. Try to match topological representations between the original data and the low-dimensional representation of the data. And that's pretty much the core of how UMAP works. But there's more you can build on top of this sort of theory. It's possible to construct representations in the high-dimensional space based on locations in the low-dimensional representation, where here essentially just inverting that optimization problem and taking a set of points in the low-dimensional space, optimizing the representation in the high-dimensional space to get as close as possible to it. It's also possible to embed to other manifolds than nice standard Euclidean space. This might be important, for example, if you know your data has underlying periodic or cyclic structures. So embedding to a sphere or a torus might actually make a lot of sense. In the bottom left-hand corner, we have a Gaussian energy embedding. So this is embedding into the manifold of Gaussian distributions. The result of that is that it embeds things not as points, but as Gaussian distributions, capturing not just the position of where it's embedded to, but a notion of uncertainty around that point. Where does that point embed to? How uncertain is the positioning of that point? On the bottom right, we have embedding to hyperbolic space. If you have, for example, a tree-like structure in your data that you want to see represented in that way. And another option, Tim Sainberg built a version of UMAP that uses all the same theory, but trains a neural network to learn a direct mapping from the input space to the embedding space. And this allows both for lightning fast embedding of new data and very powerful options for semi-supervised learning, using the topological structure of the unlabeled samples to inform the supervised training of your network. So for example, on MNIST digits, Tim was able to get a classifier to 98% accuracy using just 4 labeled samples per class. So very, very little labeled data and a whole lot of unlabeled data to learn the geometry and structure. We can also align sequences of 2D embeddings. Here, for example, are embeddings aligned in time. Each slice is a 2-dimensional UMAP embedding, but we can now see how those embeddings change and evolve over time. Finally, there's also DensMap, which allows you to capture some of the differences in local density. UMAP tends to collapse those away, as you might imagine, when you're just looking at that sort of varying size of the balls and the cover, but you can force the low dimensional embedding to learn some of that information about the local density and capture it in the embedding as well. So to wrap things up, UMAP is an effective tool for representing data, letting you see some of what's going on in your data. There's a great quote from The Hobbit by Tolkien. There's nothing like looking if you want to find something. And often the best thing to do is to look at your data through whatever means you have available. And UMAP is at least one powerful lens that lets you look at some of the structures in your data and help you ask good questions. But equally, topology provides rich foundations for unsupervised learning in general. And there's a lot of opportunities for further algorithms to be developed along these lines. To find out more, you can go to umaplearn.readthedocs.io, and there's documentation on all of this that I've talked about and more. Thank you.